Hello everyone, today we're going to create a module that lets you debounce a button. The clip you're watching now shows this module in action. Each time I press the button, the counter increments exactly once, no flickering and no double counting. This is an extremely important topic because solving this problem right lets you trigger an event from any asynchronous input in a controlled and predictable way. In this video, we will make a debouncer module that lets you safely transfer any asynchronous signal into your system clock domain. The beautiful thing is that this debouncer module only needs to be written once. Once you have it, you can reuse it forever. Just instantiate it whenever you need a clean, clock synchronized input. So to start, let's go over why we even need a debouncer. When we have an asynchronous input, such as a button, that signal doesn't switch cleanly between 0 and 1. Every time you press or release it, the mechanical contacts inside the button physically bounce for a few milliseconds, producing a noisy waveform, like this one here. So this here is what it looks like when you press it. There's some noise. And this is what it looks like when you release it. There's some noise. In an ideal situation, it would look like the one down here, where there's one clean transition up and one clean transition down. From the ideal input, we can very easily detect the edges and make pulses to trigger events off. So, the main challenge of designing a button debouncer is in making a module that takes the button and generates the ideal input. Then using the generated ideal input, we can make our pulses to trigger our events off. So the very first step is to make a noise remover module. The noise remover module will take in a noisy signal through its input port and will emit through its output port the cleaned up version of that signal. So now let's discuss how we will make the noise remover module. When the noisy signal first goes high, the noise remover module starts counting clock cycles. If the signal remains high for the full delay period, the module accepts that the input is high and stable and drives its own output high, as shown here. The same process happens when the input goes low. The debouncer waits for the signal to stay low for the entire delay period before driving the output low. As a result, the output of the noise remover transitions only after the input has remained stable for a sufficient amount of time, producing our ideal bounce-free signal. So now let's go over how the code implements the behavior just described. So this here is our noise remover module. On line 33, we have our delay parameter declared. Then on lines 35 through 37, we have our ports declared, where we have our clock, our input, and our output declared. Then on lines 39 through 40, we have our counter register declared, where its bit length is a function of the delay. Then on lines 44 through 49, we have the core logic that we discussed earlier. Whenever the input is different from the module's output, meaning that the button might have changed states, we begin incrementing the counter. The counter keeps increasing as long as the signal remains different, and once it finally reaches the number specified by the delay parameter, the noise remover accepts that new state is valid. At that point, it toggles its output and resets the counter back to 0, ready to repeat the process. Then, on line 52, we handle when the input does change, but then quickly bounces back before the counter finishes. In that situation, the counter is immediately reset to 0 without changing the output. This ensures that the noise remover only toggles its output after the input has remained completely stable for the full duration specified by the delay, giving us a clean, perfectly filtered signal each time. So now, let's look at the simulation of the noise remover. So this here is the simulation of our noise remover module, and we have our noisy button input. So when the button goes high, the noise remover module's internal counter is going to start counting. It counts up here, but then it goes back to 0, because whenever they're equal, this line executes. And we keep doing that until finally it becomes stable here. And then it counts and it counts and it counts until finally we transition there. And the time it takes to transition is, let's see, 10 milliseconds. So it takes 10 milliseconds of it being stable for it to transition. And the reason why that is because in our test bench, we set the parameter to 1 million. And 1 million at a 100 megahertz clock results in 10 milliseconds of a delay. So the delay for us with this parameter in this test bench is 10 milliseconds. And that's a great delay to have in real time too, when you generate your bit stream for this. So then, once that happens, the counter, now that the two inputs are equal, it's just resetting to 0 because line 52 is just executing indefinitely. Then finally, when the button is released, here it seems like it's released for good, but oh, nope, it's not. So then it goes back up, so it resets to 0, then jitters again, until finally here it stabilizes. So then if we go there, we get this. Then 10 milliseconds after the actual final last edge, it transitions back to 0. And then we have another one here where 10 milliseconds after it stabilizes, it asserts it high. Then 10 milliseconds after it goes low, it toggles its output low. So this here is the simulation for the noise remover module. Now let's go over how to create the top level module that uses the noise remover module to implement the full Debouncer module. So this is the top level module that ties everything together. First, it synchronizes the button input to the 100 megahertz clock using 2 flip-flops. Then it passes the signal into the noise remover, which filters out any contact bouncing. Finally, it uses another pair of flip-flops to detect clean rising and falling edges, generating single cycle pulses for your logic. In short, it synchronizes, cleans, and detects, giving you perfectly stable pulses ready to use anywhere in your design. So now, let's look at the simulation of this top-level module. So this is the simulation of the Debouncer module. So we take in our button as an input, then our noise remover module generates this button debounce signal, which is internal. Then our module generates these two signals based on the signal as our output. So we generate 2 pulses. Then we can use these pulses to trigger events, as we will demonstrate shortly. Now suppose we have this 16-bit counter module where it requires a start pulse for each incrementation, and we wanted to make it be where with each push of a button it would increment. 1 button push for 1 increment. Well, we can make a top-level module that uses our debouncer like this, where we instantiate our debouncer after having made 2 wires for its outputs. Then we take the output from one of its outputs, either one will work, but I typically prefer to use the falling edge output, and we use that output pulse as the start pulse for the counter. And by doing that, we're able to get the behavior that you saw at the beginning of this video. So if you made it this far into the video, you're clearly very interested in button debouncing. So check out the video description where you can get the code for the Button Debouncer and use it in your own projects. It is provided in the Google Drive link. That's all for this video, but stay tuned for the ones that will come out next.